I wanted to talk a little bit about capacitors because that's the next thing that y'all are doing. So I wanted to remind y'all of what a capacitor is. And so what a capacitor is any time you have two conducting bodies separated by an insulator. And a capacitor can store charge for a short period of time. It'll discharge. It's not something like a battery. It usually just has it for a short period of time. And the most common type of capacitor is a parallel plate capacitor. And in a parallel plate capacitor, you have one side is positively charged, the other side is negatively charged, and there's an electric field in the middle. And the parallel plate capacitor has a capacitance that's equal to the permittivity constant. Y'all remember that permittivity constant from physics? Actually, it is related to K, so it's 1 over 4 pi K. It's the epsilon. Yeah. So it's epsilon A over D, and epsilon naught is the permittivity of free space. Epsilon would be the permittivity of free space multiplied by some constant if you had some insulator in there. So A is the area of the plate. And D is the distance between the plates. So the other things that you need to know about capacitors is that the charge is proportional to the voltage, and that proportionality is the capacitance. And then the big thing for capacitors is that the current equals C dV dt. And you can get that by differentiating both sides of this equation right here, because the derivative of charge is current, and then you have dV dt. So I equals C dV dt. Now, on the other hand, if you then divide both sides by C and then integrate both sides, you get that V of t equals 1 over C times the integral from 0 to t of I of t dt. Plus whatever initial voltage you might have had on that capacitor. If the capacitor is uncharged, then you don't have that V of 0. The energy, which your book uses W, is 1/2 CV squared. And so the energy that's stored in the capacitor is stored because of the electric field. This next thing is really important. You don't know why yet, but trust me, it really is. The voltage across a capacitor cannot change instantaneously. But the current can. And that is very important, and we'll see why in a minute. All right. one more thing, what was it? So let's think about a capacitor. And the reason its symbol looks like this is because this is what they usually look like. They're little parallel plates. So let's say that we have a capacitor and it's not charged. When the current starts flowing, then this side will start building up a positive charge, and this side will build up a negative charge, and as it does that, it'll send the current in that direction. So when you first start up a capacitor, the current will flow right through it. But that's only right at the beginning. After it is charged, then it's just sitting there. You've got this side is plus charge, this side is minus charge, and no current is going to flow because there's like that gap in between it. And so after it is charged, it acts as an open circuit. Okay, so let's say this is our circuit. Oh, I'm going to put U of t right there. No, I'm not doing that. What am I doing? I am that's what I'm doing. So the circuit has been on for some time. At t equals 0, the switch is opened. What are the current across, the current through and voltage across the capacitor just before and just after the switch action? Okay, so what do we know about voltage across a capacitor that I said was real important just a minute ago? Doesn't change instantaneously. So if we know the voltage before the switch, we know the voltage after the switch because it can't change instantaneously. What else do we know about a capacitor that's been sitting in a DC circuit for some time? It's fully charged. Is any current flowing through it? No. So at t equals 0, not 0 voltage, 0 current. Yeah, I'll show you. It surprised me too. Okay, so at t equals 0, there's 0 voltage. 0 current. 0 current, IC. IC equals 0 amps. There's no current flowing through it. But if you look at it, it's in parallel with this 3 ohm resistor. Things in parallel have to have the same voltage. The way you find voltages of capacitors is you find something that it's in parallel with. And so before the switch action, we have 12 volts and 3 amps, and we do have this capacitor over here, but no current is flowing through it, so all our current is going through here. So the voltage across the 3 ohm resistor is 12 volts. And you can see that actually because all 3 of these things are in parallel. The voltage source, the resistor, and the capacitor are all in parallel. You could also say the current flowing through it has to be 4, and voltage V equals IR, so it has to be 12. So the voltage of the 3 ohm resistor is 12 volts, so the voltage of the capacitor at T equals 0, the voltage of the capacitor is 12 volts. After the switch, this part of the circuit is open. So it's over here, but it's not doing anything. It's there. But this was charged up to 12 volts. So when you throw that switch, this thing acts like a little 12-volt battery. And it's going to drive a current through the 3 ohm resistor. And if I had drawn my current this direction, then the current after after the switch the current is negative 4 amps. No, 12 divided by 3.
You said only if it's going the other way, or currently where it's going?
Well, it just depends on how I drew the current. So it's like I labeled the current in this direction, but the current is actually going the other direction, so that's why I'm calling it negative 4. But the voltage right after the switch is still 12 volts. So that's how capacitors act. And then, let's see, let me look at the problem that I have. So graph the voltage, current, energy, and power for a 0.2 microfarad capacitor with the following voltage. Okay.
The amount of farads have to change anything about it, or
Yeah, it absolutely does. Let's see, but that would be later when I'm looking at the. This is just instantaneously.
Oh.
So when I want to look at I equals C dV dt, right,
Okay.
then I have to use that.
Okay.
Yeah. And so I will be using that for this problem. And this will be relatively quick if y'all want to just stay for this, and then I'm going to be done. So we know what this graph looks like, or do we know what this graph looks like? The voltage. What does the voltage look like? Slope of 5, starting at 0. So 0 until here, and then a slope of 5. And then what?
At 5, or no, at 2, it has no slope.
So it goes flat. Okay, so we know current equals C dV dt. So dV dt would be the slope of our voltage graph. So it equals 5, well, it equals 0 for t less than 0, 5 for t between 0 and 2, and 0 for t greater than 2. And so our current equals 0 for t less than 0, 0.2 millifarads is 0.001 or 1 milliamp. So 1 milliamp for t between 0 and 2, and then 0 for t greater than 2. So our current looks like this. And then we want energy. Energy equals 1/2 CV squared. So that would be 1/2 times 0.0002 V squared. So, and V equals 0, 5t, and 10. So for t less than 0, it's 0. For t between 0 and 2, it's 5t. And for t greater than 2, it's 10. So that is 0.0001 V squared. So it's 0 for t less than 0. And then 0.0001 times 25t squared for t between 0 and 2, and 0.0001 times 100 for t greater than 2, or 0, 0.0025 t squared, and 0.01. Okay, so that would look like 0, and then 0.025 t squared. I know that's going to be a parabola, so if I plug in 2 for t, I get 0.01, which I was hoping I would get. So it's kind of parabola shaped, and it goes up to 0.01, and then it's just 0.01 after that, which makes sense because at that point the voltage is constant, so it's just its energy is constant. Its energy is, and this is going to be in joules. and this is time. And my current graph should, I think I labeled it milliamps. I didn't label time in seconds. And then the last thing was power. So power equals IV. So our current was 0.001, I mean 0.001 and 0, yes. And our voltage was 0, 5T, and 10. So this is current and voltage. So our power is the product of these. So it's 0.005T and 0. So 0, 2 times 0.005 is 0.01. So we just have a straight line there, and then it goes back down to 0. So this is power in watts, and that's time. And I know that she likes to have a question like this on tests. Did she have one like this on test 1? Something where yeah, no?
You didn't read it, the first page. And you had to like just read it and do like a derivative or something.
Okay,
But it wasn't like you had to graph it.
Okay.
I think she said you would have to graph it.
that you would have to graph it?
She said something about it.
So I would think this one is going to be about as straightforward as they get. The others that I have examples for are, have more difficult computations. So I would expect something like this would be on a test, because you're not going to want to be doing like ridiculous integrals and derivatives on the test. So I think this is kind of a good one to know.
Do you think she would care if, like, you don't have the sign that includes like the number? So you see how like it says 5t 0 less than, or t is greater than 0 but less than 2.
Yep.
You don't need like a line under any of those, like.
Oh, like which side is equals?
Yeah. Do you think she'll care about that?
I don't think so. To me, it seems like engineers are like don't care as much about that as math people do. With voltages though, they should always be equal, because it's never supposed to change instantaneously. And so they should all be equals, but it doesn't really matter. I think it'll be fine. All right. Thank y'all so much for coming and for staying.